All right, so I have been introduced to some of the most awesome people I have ever seen in my whole life. They're called the Amoeba people, and they make science songs. This one's linked on your canvas. It's all about the continental drift theory, which is what we're talking about today, and a guy named Alfred Wegener, and it tells his story much better than I can. So please watch it. I'm still not sure if when I play a video you'll be able to hear it. So I linked it onto the Canvas page along with another helpful video. Please check them out after you're done with this lecture because they are really good at explaining it just a little bit more than I do, and it gives you another exposure to the material, helping you remember it, so take advantage of the resources you've been given. Bell ringer today, please explain convection to me. Hopefully running through your head, you should be able to look at this diagram and think, yeah, this is convection, this speaks convection to me. So we should, I hope you know from our layers of the earth lecture yesterday that the Earth's core is really, really warm. And so what that does is that heats up the semi-liquid, semi-turbid rock right here in the mantle. And we know that warm things are less dense, so they rise. So it's going to rise up to the top here. And then as it gets to the top, it's going to cool down because it's away from that heater right here, the core. So it's going to cool, and we know that cool things sink, so it's going to sink back down. And it's going to be warmed up by the core again, and it's going to rise, and it's going to go down again because it's going to cool, and so on and so forth. And what we get here is a couple of crust features that we see. They're typically under the ocean. But this one specifically, this is definitely under the ocean. It's called an ocean ridge. And what happens is as this mantle, the warm mantle is moving along the surface right here, it pulls these plates. And it can even leave, some of the liquid can leave here and we can form new crust, and it starts to move this way and pull it this way. And so as it's pulling it this way, this magma or lava, the molten turbid liquid rock right here, fills this space and cools and becomes new crust, and then eventually that moves and is pulled away. And then the earth isn't constantly growing, because if you just left it at that, we would think, the earth is always growing. That's so odd. Why is the earth doing that? But it's not. We can see down here, this is called a subduction zone. One of the Earth's plates is caught up underneath another of the plates, and as it pulls and diverges right here, these two are colliding, coming together, and it pushes this plate underneath where it'll eventually melt and become part of this mantle liquid. But anyways, that's convection. The convection is actually, that was a lot, but the convection is the rising of heated mantle material, and then it goes towards the crust, and then it's going to cool down and it's going to fall, where it's going to be warmed up again by that core, and it's going to rise because it's less dense, and then it's going to cool down, becoming more dense, then it's going to fall, and it's this circle, it repeats itself again and again and again. And we've got a bunch of these convection currents inside the earth at any given time. This is the other video I linked to your Canvas page, Pop-Up Pangea. It really talks a lot about what we're learning today, so check that one out too. The first one was more fun and how will help you remember. This one's going to give you some great visuals. We're going to look at this guy. His name is Alfred Wegener. He is the scientist who proposed the new idea of the continental drift in the early 20th century. He proposed, or he suggested, that the continents have once been joined. This is something we know to be true today, but at the time, like with many scientists, the scientific community didn't believe it. They were like, no way, this isn't happening. That can't be possible. Where's your evidence? Like, it's great that you say that, but I want your evidence. Because he couldn't really explain why it was happening at the time, he was pretty much dismissed and told, you don't know what you're talking about. And that's, fortunately, as the song says, how he died. Eventually, we learned that what he said was true, and we now credit him with the proposal of the continental drift theory. So, Alfred Wegener, proposed the continental drift theory. Here's more on that. I didn't link this one. It's just short, sweet, and simple. I think the Pangea pop-up is much better, but we'll watch this in class too. It goes over what the continental drift theory actually is, but we're going to learn about it right now. What the continental drift theory says that the lithosphere is the rigid outer part of the planet. We know that we live on the lithosphere. That's what we're studying right now. It's made up of the crust and the upper mantle. So if you can see right here, we've got continental crust and oceanic crust, and then we've got just a little bit of mantle right there. That's the lithosphere. And it says, or the continental theory suggests, that this lithosphere, so the crust and a little bit of the upper mantle, is broken into tectonic plates. And these plates move over time, slowly, because we learned that this part right here is moving and grooving because we've got convection currents in there. So this liquid rock is moving all over the place. And as it moves, it brings with them those floating plates with it. So that's why we get movement of our tectonic plates over time, because of this movement of the convection of the mantle liquid. So that rising of the warm mantle liquid and the falling of it when it cools down and the rising of it, that is what causes our plates to move. Think of like a styrofoam plate on the ocean as it's being moved around. That's kind of like what the tectonic plates are doing. Kind of. When the continents are in constant motion, whether you realize it or not, they move at a rate of centimeters per year. And they form, they don't form. At one point, 335 million years ago, there was what we call a supercontinent, or the land that we know of, like Africa and Europe and Asia and Australia and North America and South America. They were all stuck together in one giant supercontinent called Pangaea. This was 335 million years ago, so a way long time ago. You learned about this in Earth and Environmental Science when you studied the Earth's history. You learned that this broke apart in about correct me if I'm wrong, but a little bit before the time of the dinosaurs. So a little bit before the Mesozoic time or era. Fantastic. So Alfred said that a long, long time ago there was once a supercontinent called Pangaea. He said that it moves because of the plates right here on Earth, and as they move across the flowing ooey gooey mantle, where he said the lithosphere is broken into 8 major plates. Or he might not have said 8 major, but he did say it was broken into these plates. We now know through further research and a little bit more scientific stuff that there are 8 major and we have many little minor plates. Why? Again, we talked about this. The plates are on the planet's surface, move because of the convection currents of the mantle. Hot material rises and cool material sinks. We know that, the density differences. We studied that in the hydrosphere. But as that warm mantle comes up, it eventually, because it's less dense, it rises. And then as it cools, it becomes more dense, and we know that more dense things fall. So it's falling back towards the middle of the Earth, where it warmed up again and it becomes less dense, and then it rises towards the crust. Then it cools there and it becomes more dense and it falls back towards the core. So that circular movement, those convection currents, are why we have the movement of tectonic plates. Now we know all this now, but Alfred didn't know that back in his day, which is why he wasn't accredited this theory when he was alive. Eventually we realized, yep, you were right. You were absolutely right. And we now credit him with it, but unfortunately he did not get to reap the benefits of that. But that's why the tectonic plates move. It's called the continental drift theory. Got another video for you. I'll link this one in your Canvas page so you can watch it. It sums up what we're talking about, and it really shows how that mantle the flowing mantle plays a part in the movement of these plates. Now we know if you look back here, you can see one of the fault lines that we know of. It's called San Andreas Fault, if I'm not mistaken. It's the boundary between this plate and the North American plate. And we know that living in North Carolina, we don't experience that many earthquakes and whatnot, but we do know that in California they experience many more earthquakes. A lot of that has to do with their proximity to this fault line, where those tectonic plates are bumping into each other and moving away from and towards and whatnot in all kinds of directions. And that movement of the plates and the bumping into one another is what causes those earthquakes. But we're going to study earthquakes another day. I do have one final thing to teach you. We're going to learn about the different types of boundaries. There are 3. The very first one we learn, so they are tectonic plate boundaries, so the boundaries between 2 plates. So our plates, like this plate and this plate, actually we'll do these 2 plates again to go back here. So we know that these are convergent boundaries, so that we know that when these 2 plates are interacting, they are pounding into each other, they're colliding into one another. We know that with this one right here, that it's a divergent boundary, meaning that these plates are moving away from one another. Good. Okay, so our first type of boundary is called convergent. Convergent means colliding. I have a song for you that we will sing at the end, but a convergent boundary is where 2 plates are moving towards each other. Plates can push up to form mountains, or one can slip below into what we call a subduction zone. So we form mountains at convergent boundaries. We actually form mountains at all the boundaries, but convergent boundaries are how we formed the Appalachian Mountains here in North Carolina. 2 plates hit each other a long, long time ago, and that's how we got the Appalachian Mountains. We'll learn about that on Thursday, though. So convergent means colliding. Divergent means dividing. A divergent boundary is where 2 plates are moving away from one another. New crust forms at a divergent boundary. This is where our ridges are, because the magma rises to the surface between the 2 plates. So as these 2 plates pull apart, the magma that's underneath, the lava that's the mantle material, seeps up and through and fills in this space right here. This is what happens at oceanic ridges, so that new crust is formed at the very edges of the divergent boundaries, and then they keep pulling apart, and new crust is formed on top of that, and new crust is formed on top of that, and so on and so forth. The moral of the story here is divergent means dividing. The plates are moving away from one another. And lastly, our weird one, transform. Our transform boundaries, our plates are sliding past one another. Transformant boundaries are where plates slide sideways past each other. As the friction and pressure builds, it can release in the form of earthquakes. So transforming is sliding. Now, I've got a song for you, and I'm going to periodically ask you to sing the song because it is such a good way to remember these 3 types of boundaries. Let's see if I can turn on my video. I don't know if I can right now. Okay, I cannot figure out how to turn my video back on for this. I will just sing it to you and you won't be able to see my face. But it goes along to the Addams Family song. Goes, what is the Addams Family song? I don't even remember the real words to it. It goes like, da-na-na-na, 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 da-na-na-na. Transforming it, hang on. Convergent is colliding, divergent is dividing, transforming is sliding, and that's the boundaries. Ba-da-da-da, ba-da-da-da. Convergent is colliding, divergent is dividing, transforming is sliding, and that's the boundaries. Da-da-da-da, da-da-da-da. So practice that song, please. And I've got some movements with it, which you can't see, but convergent, I take my fists and I pound them together, smash them into one another like I'm giving a fist bump. Divergent, I take those 2 fists that are together and I pull them apart. We're dividing. Transforming is sliding, so I kind of slide my hands past one another because the plates are sliding past one another. So practice that. That will be your bell ringer tomorrow. Okay, guys, have a great day. I hope you enjoyed learning all about plate tectonics, Alfred Wagner, and the different plate boundaries that form at each of these tectonic plates where they meet. If you will, watch that Alfred Wagner video just one more time. Perhaps play it in the morning as you're eating your Cheerios or in the evening as you're brushing your hair. It is a good way to review what you know. Have a great day, guys.